This is section 4.3 of your calculus textbook. We're going to talk about connecting f prime and f double prime with the graph of f. In this section, we're going to find out about the first derivative test for local extrema. We're going to learn about the concept of concavity and points of inflection. We'll learn about the second derivative test for local extrema. And finally, we'll learn about functions from their derivatives. This video will focus on the first derivative test for local extrema. We're not going to have any new definitions, but we will have a new rule, which is the first derivative test for local extrema. Let's get started. Notice the graph at the bottom and take a look at it a little bit as we read the paragraph above. We see once again in this figure that a function may have local extrema at some critical points while failing to have local extrema at others. The key piece is going to be the sign of f prime in a critical point's immediate vicinity. So as x moves from left to right, the values of f increase where f prime is positive and decrease where f prime is negative. Before we get too deep into this, let's take a look at the key features of the graph below. We have critical points every time that f prime is equal to 0 or f prime is undefined. Notice that those occur at all 5 of the C values. Here, 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 and there. Notice that we have a local maximum at 1. We have a local minimum at another. Both of these share the condition that f prime is 0. There's another absolute max as well, but at this point, f prime is undefined. Notice the graph comes to a point. There are two other critical numbers here where there is no extreme value. There's not one at C1 or at C5. And we see here that the graph kind of continues to move up or continues to move down at C1 and C5. The key to whether f prime undefined or f prime 0 is going to be a local max or local minimum has to do with the sign of f prime right around that point. Notice that on the local max to the left, we have f prime positive, the graph is increasing, and to the right, we have f prime negative, the graph is decreasing. At the local min, right to the left, we have f prime negative, to the right, we have f prime positive. So let's get into that a little bit more. At the points where f has a minimum value, we're going to see that f prime is negative on the interval immediately to the left. So f prime is negative to the left, and f prime is positive on the interval immediately to the right. And if that point happens to be an endpoint, then there's only an interval on the appropriate side. If it's a right endpoint, look to the left. If it's a left endpoint, look to the right. So here's what that means. The curve is falling on the left side. That means f prime values or that means f is decreasing. And it is rising on the right side. That means the values are increasing. Let's take a look at a local min. Here's the first one that jumps out at me. Notice to the left, f prime is negative, and that indicates that the graph of f is falling. It also indicates that all of the tangent lines have negative slopes, and I think that's pretty easy to see. To the right, we have f prime positive. Notice that the graph is rising to the right of the local min, and that also means that all of the tangent lines have positive slopes, and again, that's pretty easy to see. We have local minimum on the right side of the curve as well, and notice there is no curve to the right of that right side of the interval, so that we only need to look at the left side. We have f prime negative, so the graph is falling, and that gives us a local min there to the left. So what's the key part? Well, we have a critical number. We have f prime negative to the left. We have f prime positive to the right. Let's move forward. If we look at the local maximum values, we're going to notice that f prime is positive immediately to the left, and that f prime is negative immediately to the right. So what does that mean? It means that the curve is rising on the left of the critical point and it is falling on the right. Here's a local maximum value. Notice that to the left we have f prime is positive, so the graph is increasing, and that means that all of the tangent lines have positive slopes. Notice that to the right, f prime is negative. That means the graph is falling or decreasing. And that also means that all of the tangent lines have negative slopes. And that's a key piece. To the left of this local max, f prime is positive. To the right, f prime is negative. It's going to be true over here for the absolute max, which is also a local. F prime positive to the left, the graph is rising. F prime negative to the right, the graph is falling. So we put all of that together and we get a theorem, the first derivative test for local extrema, and it's going to take us a few slides to get through it because there are several pieces. It goes like this. The test applies to a continuous function f. So first we have to have a continuous function. At a critical point C, number one, if f prime changes sign from positive to negative at C, then f has a local maximum value at C. So take a look at this. Here's f prime is 0. So we have a critical number in the first example. We have f prime is positive to the left. We have f prime is negative to the right. The graph is rising, the graph is falling. That makes this point a local max. On the graph to the right, we have f prime is undefined, so that means that it's not differentiable, and we see that there's a cusp on this graph, but the same part of the test applies. To the left of that point, f prime is positive, the graph is rising. To the left, f prime is negative, the graph is falling. That makes this, again, a local max. Next, number 2, if f prime changes sign from negative to positive at that critical value, then f has a local minimum value at C, and we see that. F prime negative to the left, the graph is falling. F prime positive to the right, the graph is going up or rising. That makes this point at C a local min. We have the same thing to the right, except this time the graph of f is not differentiable at C, so f prime of C is undefined. We have the graph falling to the left, rising to the right. F prime negative changes to f prime positive, so we have a local minimum. As we move forward, if f prime does not change sign at a critical point, and this is also possible, then we do not have a local extreme value there. We see on the first graph here to the left that we have a critical point, but we have f prime positive to the left and then f prime positive to the right. So it changes from rising to rising at the critical point. Therefore, we do not have a local extreme, and the same to the right, except f prime is undefined. We have f prime negative, the graph is falling, changing to f prime negative again, the graph is still falling, no local extreme. If we're looking at a left endpoint, all we need to do is look at the right side of that endpoint in the interval. If f prime is negative, meaning that the graph is decreasing, we have a local maximum. So I'll write that in, local max. If we have f prime positive to the right of that left endpoint, the graph is rising, then we have a local min. Same thing goes for a right interval. We only are a right side of the interval. We only look at the left side of that point. If f prime is negative, meaning the graph is decreasing or falling, we have a local minimum value. And if f prime is positive, meaning the graph is rising or increasing, then we have a local max. So what does the first derivative test allow us to do? It lets us know when we have local extreme based on the first derivative. So here's how we apply it. First, the critical points of a function f are going to partition the x-axis into intervals on which f prime is either positive or negative. So that's key. The first thing we want to do is find the critical points of a function and use those critical points to partition the x-axis. Next, we determine the sign of f prime in each interval by evaluating f prime for one value of x in the interval. I usually refer to this as a test value. We'll see it on the next example. Then we apply the first derivative test as shown in the previous slide. So all those purple boxes in the last few slides, that's the first derivative test. We're going to apply it last. We're going to see that here in example 1a and 1b. So for each of the following functions, we want to use the first derivative test to find the local extreme values. Then we want to identify any absolute extrema. So let's start with part A. F of x is x cubed minus 12x minus 5. Step 1, we want to find any critical points. So let's go f prime. That's going to be 3x squared minus 12x. Critical values are where the derivative is 0 or undefined. It's possible this is 0. Let's go ahead and solve. So we'll take out a 3. That leaves us with x squared minus 4. I messed up the derivative here. That should be just minus 12. So then x squared minus 4, set it equal to 0. Keep factoring. X squared minus 4 factors into x minus 2 times x plus 2. So that means we have a critical value at x equals 2 and another critical value at x equals negative 2. So then we draw a number line. We're going to refer to this as a sign chart. This is your x value, or your x-axis. It moves from negative infinity to positive infinity. We're going to make tick marks and partition the x-axis at the critical value, so at negative 2 and at positive 2. Now we have 3 intervals on which to test the sign of f prime. The interval from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. We are testing f prime. It's important that we label this sign chart so that our reader knows exactly what we're doing here with the sign chart. We're looking at f prime. So we're going to pick a test value in one of these intervals. For instance, in the first interval, I might pick, say, negative 3. That might be an easy number to plug into f prime and figure out the value. So if I do that, if I plug in negative 3, say to this equation, I get 3 times a negative 3 squared minus 4. Well, negative 3 squared is 9. 9 minus 4 is 5, and 3 times 5 is 15. I'm going to write here f prime of negative 3 is 15, but that's really only just some scratch work. What's important here is that 15 is positive. So I'm going to write a plus there, telling me that f prime is positive. Between negative 2 and 2, I might pick the x test value of 0. Let's plug that into the function's derivative. So that would be 3 times a 0 minus negative 4. So 3 times negative 4 is negative 12. My scratch work here is going to say f prime of 0 is negative 12. But what's important is that f prime is negative. Then I've got a test value from 2 to infinity. I'm going to choose 3. So I'm going to plug 3 into the function. I'm going to get 15 again. So the sign of f prime is positive. So what does that mean? Well, when f prime is positive to the left of negative 2 and negative to the right of negative 2, the graph rises to the left and falls to the right. Then at the critical value 2, the f prime is negative to the left. We're falling. Positive to the right, we're rising or increasing. So here we are, rise, fall, rise, and you can almost start to see the shape of the graph. You kind of continue these arrows to show that we have absolute extrema. So what are those absolute extremas? We have an absolute maximum at x equals negative 2, and we have an absolute minimum at x equals 2. And we did that with the first derivative test. We took a look at f prime. Let's move to part B. G of x is x squared minus 3 times e to the x. So we need a product rule for this derivative. G prime of x is equal to the first function, x squared minus 3, times the derivative of the second, e to the x, plus the second function, e to the x, times the derivative of the first, 2x. I'm going to factor out an e to the x from both of these terms, e to the x out. That leaves x squared minus 3 in the first term. That leaves 2x in the second term. So if we rewrite this a little bit neater, we have e to the x times an x squared plus 2x minus 3. Critical values are where this is equal to 0. So we're going to solve, and I can do that by factoring. We'll leave the e to the x here. X squared plus 2x minus 3 factors into x plus 3 times x minus 1, which gives us a critical value at x equals negative 3 and at x equals 1. Let's do our sign chart. We go from negative infinity to infinity on the x-axis. We are going to make a partition at negative 3 and another partition at 1, and we are testing the sign of f prime. So let's pick a value in the first interval. I'm going to choose negative 4. If negative 4 goes into, say, this piece or this version of g prime, e to the negative 4 is positive. Negative 4 plus 3 is negative, and negative 4 minus 1 is also negative. So we have a positive number times a negative number times a negative number. That makes f prime positive. Let's go to the second interval from negative 3 to 1. Choose a test value. I'm going to choose 0. If 0 goes into the same line of g prime, e to the 0 is 1, so that's positive. 0 plus 3 is 3, that's positive. 0 minus 1 is negative 1, that's negative. So we have a positive number times a positive number times a negative number. That makes f prime negative. Then from 1 to infinity, I'm going to choose a test value of 2. We plug that into the same line. We get e squared is positive. 2 plus 3 is positive. 2 minus 1 is positive. Positive times positive times positive is a positive number. So there we have it. In the first interval, the graph of f increases. In the second interval, the graph of f decreases. In the third interval, the graph of f increases. So what do we have here? We have, well, let's connect those arrows. Looks like we've got an absolute max. Looks like we've got a local max and a local min. And I just realized now that I labeled these wrong in the first part. So let's go back and change those to local. There we go. And here, let's give an answer again. We have a local max at x equals negative 3, and we have a local min at x equals 1. Exercise 3 is the next slide, but I'm going to leave that one to you and to class time, and that wraps up the first video of this section.